Good day, sir. My name is Akiwa Nyatela with student number 145799820. I am currently studying an advanced diploma in civil engineering at University of South Africa. As a part of the learning process, we were tasked to complete a project that will entail the full design. This project it's an upgrade of a gravel road to a surface 4-lane divided road. So what I did for when I was doing my research, I decided that I'll select a municipality and a township in this municipality, and then I'll take their main road as for my project. So I'll give you the name of the municipality, the name of the township, as well as the name of the road. Alright, so I'll be taking you through my presentation. Here is my PowerPoint presentation. The introduction. The Castell Township is situated within the Maluti A Pofong local municipality in the Free State area. Is experiencing a significant growth and development. Mampoi Road, which is currently a gravel surface, requires upgrading to meet increasing traffic demand and improve road safety. So in line with the municipal's infrastructure improvement strategy, the Maluti A Pofong municipality project management team appointed a civil engineering technology. In this case, the civil engineering technology, it is myself, Sakiwa Nyatela, to undertake the design of the Mampoi Road and produce a comprehensive design report for its upgrade to a dual carriage way. Alright, so project location. As I indicated, that I decided to select some municipality, township, as well as the main road. It's indicated there is a name of the road, and then there are coordinates, start coordinate, and then the end point coordinate. Okay, so the next slide, project data and condition. So I'll focus on 2 points here, terrain classification and subgrade strength. So if I start with the terrain classification, the Mampoi Road project is located within a mountainous terrain zone. This classification impacts the geometric design, earthworks, and drainage provision in accordance with the geometric geometric design standards for the mountainous region. And then the next one is the subgrade strength, which is CBR data. California bearing ratio, which is CBR values, were obtained along the center line for both westbound and eastbound carriageways. The results are as follows. Let me take you through the results. So I have taken a test in 18 stations. So the test point 1, it was 4%, or the CBR is 4%, test point 2, 5%, test point 3, 4%, test point 4, 5%, test point 5, 6%, test point 6, 8%, test point 7, 9%, test point 8, 13%, test point 9, 10%, test point 10, 14%, test point 11, 13%, test point 12, 14%, test point 13, 19%, test point 14, 20%, test point 15, 22%, test point 16, 18%, test point 17, 19%, and test point 18, 23%. The next slide is about the climate conditions. Climate conditions, according to THR4 classification, the area is categorized as a moderate climate region. However, the area experiences significant seasonal variation in rain. Rainy season duration approximately 9 months annually. Peak rainfall month January, with an average rainfall of 119 millimeters. These conditions necessitate robust drainage and pavement design to mitigate the effects of the moisture on the subgrade and pavement layers. Alright, overview of the adopted geometric design software. The design of Mampoy Road was taken using Civil Designer, a specialized civil engineering software package that supports building information modeling for infrastructure projects. Civil Designer offers an integrated platform that enables organizations of the project data for efficient project management, creation and analysis of digital terrain models to accurately represent site conditions, design and analysis of surfaces for optimal earthworks and grading solutions, development of rural layouts and corridors in accordance with the geometric and pavement design. Alright, road reserve requirements. A road can be defined as a wide strip of land designated to accommodate all the cross-sectional elements necessary for safety and efficient vehicular movement. The land required for this purpose is referred to as the road reserve. For this type of the roadway, the road reserve requires typical ranges from 30 meters to 50 meters, with a standard allowance of 30 meters, commonly adopted for design purpose. In terms of the functional classification, the Mampoy Road falls under Class 3, which is the collector road in a rural region. This classification reflects its role in linking local roads to higher order roads, while also facilitating access to adjacent properties and connecting to township road networks. Alright, the data input into geometric design. So I'll be taking you through 8 steps. So I'll start with step number 1, which is import points. Roads coordinates were obtained from the Department of Transport and imported into Civil Design. A digital terrain model of the road surface was generated from the important survey points. The proposed horizontal alignment was created along the existing 4-lane corridor. A road corridor assembly was generated along with alignment incorporating the cross-sectional elements. Longitudinal sections were produced from the alignment to analyze vertical profiles. Cross-sections were created at regular intervals to detail the road geometry and pavement layer. Side drains and culverts were designed based on the road surface and anticipated drainage requirements. Road signage and pavement markings were incorporated into the design in accordance with the relevant standards. Okay, the next few slides will be screenshots that were taken from Civil Designer during the design. Alright, the screenshots of the data input into the Civil Designer. Here is a screenshot. I'm sure you will see it. It's X coordinates, Y coordinate, and Z coordinates. Alright. So this is just a continuation of the data input into Civil Designer. Yeah, this is the road layout. Alright, the next one, horizontal alignment curves. You can see there is the information there. Horizontal alignment, road 1, which is that's a road that we're referring to, the Mampoy Road. The next one, selecting the carriageway and input the slopes of the proposed road. Okay, here is a screenshot that is showing the slopes. As I showing you on my screen, you will see that's a carriageway setup. It's got the campus. Alright, the next screenshot, selecting adopted pavement layers on the software. So you see the granular bases there. Here are the layers, the G1, C3, etc. Alright, this screenshot is just showing for the new VPI. Here is the detailed information. So this is the vertical alignment in the road and ensure that the curve length is adhered to the minimum of 140 meters as per the TR817. Okay, and then the calculating the volume for cuts and fill. Here is our screenshot that is showing the subgrade cross section, DTM surface, and other information. The next one is going to be the geometric design calculation. So I'll take you through the calculations. So change of the curve starts at 1,115 meters and at 1,285 meters. Grade 1 it's minus 2.5% and grade 2 is 2.5%. The BVC tonnage is 1,115 meters, as we know. BVC elevation is 1,672 meters. Excuse me. And then the vertical curve length is 170 meters. So the formula to calculate the PI, it's G1 equal to PI elevation minus BVC elevation over L over 2, and then we'll start substituting. We know what G1 is. G1 is 2.5%, needs to be converted to the number we're going to be dividing by 100, is equal to PI minus 1,672 over 170 over 2, and then we'll get our PI elevation, which is 1,669.875 meters. And then the next one will be calculating the EVC tonnage. So EVC tonnage is straightforward. It's EVC tonnage plus the length. So the length we're given there we're given the vertical curve length already, that is 170. We were also given our BVC tonnage. So you just add or combine the two, and then it will give you the EVC tonnage, which is 1,115, and then you add the length 170, it will give you 1,285 meters. And then now we need to calculate the EVC evaluation. We know our grade 2. We know the PI now since it was calculated above. Excuse. So G2 is equal to EVC elevation minus PI elevation divided by length over 2. We know our length is 170, so it's 170 over 2. Okay, then we substitute our G2, it's 1.25% over 100 to convert it back to the number. EVC elevation, it was calculated on top, it's 1,285, and minus okay, I'm making a mistake there. EVC elevation was not calculated, but we need to calculate the EVC elevation. Then it's minus the PI that we calculated on top divided by 170 over 2, which is 85. And then our EVC 11 is going to be 1,670.938 meters. Alright, and then pavement structure design standard and guideline used. Guidelines for road construction material TRH14 of 1985. Structural design of flexible pavement for inner urban and rural road TRH4. Standards, it's South African Pavement Engineering Manual. The centerline subgrade CPR values was taken at the interval of 100 meters in both directions, westbound and eastbound. Alright, the next screenshot is just a continuation of the pavement design calculations. They will be detailed in our report. Alright, the next one is also the calculation of our design structure, of our pavement design, of our pavement structure design. It's going to be detailed on the report. I don't want to bore you with those details. Alright, and then the traffic analysis and projection. Traffic data, current ADT per lane is 756 vehicles per day per lane. Road category is class B. Design period 20 years. Traffic growth 4%. This one was obtained from TRH4 table 10. Heavy vehicle percentage 2.03%. Growth factor in 20 years is estimated to be 4%. Alright, there is another information there where we calculated AADT for 20 years, which is equal to 1,656 vehicles per lane per day. Alright, I'll go to the next slide. Pavement design alternatives. So there are alternatives that are given here, which is subgrade 1, class B in the moderate region. Here is the information, the layer. Okay, here there is the information which including the layers and the MOD, ASTOS, etc. And then this is just the continuation of the alternative, the screenshot of the granular basis. Okay, and then I'll go to alternative 2. There is information for alternative 2, 150 millimeter grade 10, 90 meter much ASTO, etc. There is a screenshot there. Okay, alternative 3. There is the information provided on the presentation, as well as the cemented base table, and then we highlighted what is selected, which is it's number B on this one. Alternative 4, there is the information of alternative 4 as well, and then same applies the westbound McCarthy base, where we selected what we have used for our design. Alright, drainage conceptual design. Design standard or guideline manual use. Central drainage manual. In the road design, it is very important to make adequate provision for drainage system. The drainage system is essentially in the road structure. Below is the requirements of the road drainage system. The side drainage should have sufficient capacity and longitudinal slope to carry away all the surface water collected from the roadway. Road reserve drainage requirements. A road drainage system must satisfy two main criteria if it is to be effective throughout its design life. Okay, here are those criteria. The first one, it must allow for a minimum of disturbance of the natural drainage pattern. It must drain surface and subsurface water away from the road and dissipate it in a way that prevents excessive collection of water in unstable areas and subsequent downstream. Alright, slide 31, drainage. We're continuing with the drainage concept. Subsurface requirements. Subsurface drainage is a system of removal of excess underground water from the soil. There are generally two types of subsurface drainage, which are open and pipe drains. Open drains they can receive overland flow and thus can also use for surface drainage. However, open drains are loss of land. The surface system that is suitable for this type of road is pipe drains. Okay, here is my last slide for the presentation. Pavement alternatives selected. Surfacing. Due to the high traffic volume on the road, asphalt surfacing is the only viable option. A continuously graded asphalt with conventional binders, 60-70 penetration grade bitumen of minimum thickness 30 mm is proposed. Base layer. Alternatives considered were the following: G2 crushed stones, C3 stabilized layer. G2 is crushed stone compacted 89. Okay. G2 crushed stone compacted 89% of apparent density is proposed. It is a proven and affordable option for high volume of traffic. That's the end of the presentation, sir. Thank you so much for giving me this opportunity to present. Thank you. I am stopping the video.